Okay, so now we've seen a little bit about alcohols, phenols, thiols, and ethers. We've talked about some key features such as the functional group of interest, the OH group for alcohols and phenols, the SH group for thiols, and the COC group for ethers. Now that we've seen a little bit about all of them, and in particular a fair deal, probably more than you wanted to see about naming these things, let's move into another aspect of at least some of these compounds. Okay, as you see here, we've excluded somebody. This time here, now that we're looking at physical properties, we're going to look at the alcohols, phenols, and ethers. So everybody with an oxygen group, or at least an oxygen as part of their functional group. We've excluded the thiols for now. Those were the SH groups, and we've changed things up a bit, and we'll take a look here at these oxygen-containing compounds in this chapter lecture. Okay, so classifying alcohols can be an important way to predict their physical properties. Alcohols can be classified as primary, which we denote as that 1 prime. It looks like the degree symbol there after the Arabic number 1. A primary alcohol has one alkyl group attached to the carbon with the OH group. So a lot of those 1-ols, so 1-propanol or 1-pentanol, these would be examples of primary alcohols. Secondary alcohols, 2' there, which has 2 alkyl groups attached to the carbon with the OH group. So if we looked at, we couldn't just say propanol. Remember, we could have a 1-propanol where we had the OH group on a terminal carbon, and that would be a primary alcohol, or we could have the OH group in the middle carbon there, isopropanol or 2-propanol, as IUPAC would call it. And that's an example of a secondary alcohol because the carbon that bears the OH group in 2-propanol also has a bond to 2 other carbons. Finally, tertiary, the highest we can go. We can't go to quaternary because carbon can only make 4 bonds, at least for stable compounds that we'll see in our course. So therefore, if one of the bonds is to an OH group, the carbon only has 3 other bonds to make. So that's why we max out at tertiary, where all 3 of those other bonds are to alkyl groups. And so this would be something like a tert-butyl alcohol. So you have the carbon of a tertiary butyl group, and so that carbon is bonded to 3 other carbons. In that example, it would be 3 methyl groups, and then to the OH group for tert-butanol or tertiary butanol. So primary, secondary, or tertiary alcohols will have different physical properties. Probably much easier to see in this graphic than me trying to talk through it in the previous slide. There's a primary alcohol, so the carbon that has the OH group is bonded to one other carbon, in this case a methyl group, and then those other 2 bonds in this case happen to be to hydrogen. So that's ethanol, our good friend for those of us who may choose to imbibe when we're of age. That's the alcohol that we tend to drink. It's a primary alcohol. Secondary alcohol, 2-propanol. So we see the carbon that has the OH group has a bond to a hydrogen, and then 2 other bonds to carbon groups, methyl groups in this case. And this is an alcohol that we should not ever drink. Isopropanol or 2-propanol is very dangerous to humans in very small amounts, and it just should not be consumed like the ethanol can be consumed in relatively small amounts with relative safety. Finally, tertiary alcohol, 2-methyl 2-propanol, or this is also known as tertiary butyl alcohol. It's an example of a tertiary alcohol. The carbon containing the OH group is also bonded to 3 other carbons, the maximum that it can be. So no CH bonds in a tertiary alcohol because you have the COH bond and then CC bonds for the remaining 3 positions. So there you have it, a visual of those 3 types of alcohols, and probably a much clearer explanation than what I spent time on the previous slide trying to get across. Okay, so now that you've seen examples of primary, secondary, or tertiary alcohols, let's see how well you do with classifying, and especially for A and B, classifying just based on name, which can be particularly tricky because first you have to draw the correct structure, and then from that structure that you've drawn based on the name I've provided, determine whether or not it's an example of a primary, secondary, or tertiary alcohol. So for A, that's two different ways of naming the same thing, right? Isopropyl alcohol is the common name, 2-propanol is the IUPAC name, so there's just one compound there, two different ways of naming it that I've provided. And then B is 1-butanol, and C and D are those structures. So please go ahead and stop the video here while you classify each. You don't have to draw them if you can tell from the name, but at this point it wouldn't be a bad idea to draw them just for the extra practice, and then classify them as primary, secondary, or tertiary. Start back up when you're ready to see how you did. Good luck. Okay, so hopefully you were able to draw that structure and see whether you called it isopropyl alcohol or 2-propanol. Your carbon in the middle there, your carbon 2, bears the OH group and has bonds to two other carbons, making it a secondary alcohol. For B, 1-butanol, the OH group is on that first carbon, which is bonded to only one other carbon, carbon 2 of the butanol, so therefore it's a primary alcohol. C, we have an example of a tertiary alcohol. We can look at that sort of letter T there at the end of the molecule. That carbon at the center of our T is bonded to the OH group. It's also bonded to those two methyl groups, and it's bonded back to carbon 2 there of the structure as well. So that carbon is bonded to three other carbon groups plus the OH group, making it a tertiary alcohol. Finally, D, being a cyclic alcohol, it's a secondary alcohol. Whenever it comes off of a ring, it's got to be at least a secondary alcohol, because that, in order to close the ring, that carbon has to be bonded to at least two other carbons. So there we have it. Hopefully that went well for you. If not, if you're still struggling and frustrated, please do try some other end of chapter problems, and then reach out to me for help if you're struggling with primary, secondary, tertiary alcohols. Okay, so why do we care so much about primary, secondary, tertiary alcohols? Well, we care about alcohols in general because they tend to be fairly unusual organic compounds in that they can form hydrogen bonds within themselves between different molecules of the alcohol, and they can also often form hydrogen bonds with water if their alkyl group, the C portion is fairly small and the hydroxyl group is fairly available. They can also form potentially hydrogen bonds with water. So methanol and ethanol, these mix very well with water because they're small. They also have much higher boiling points than alkanes and ethers of similar mass because of the hydrogen bond interaction being strong. They're able to have much higher melting points and boiling points than you'd expect. Just like water has a very high melting point and boiling point for a small molecule, the alcohols, because of the significant hydrogen bond interactions, have very high melting points and boiling points compared to the alkanes or the ethers of similar mass. Now, if we look at ethers, on the other hand, they tend not to be able to form hydrogen bonds, at least not with themselves. They do have that oxygen with lone pairs of electrons. They could theoretically be hydrogen bond acceptors with water if they're in small amounts. So things like dimethyl ether might mix a little bit with water because of that. But compared with the alcohols, they have no ability to hydrogen bond with themselves. So in terms of the pure ether, they can't form hydrogen bonds between other ether molecules, and as a result, they have much lower boiling points and melting points than the alcohols would be, but they tend to be pretty much in line with alkanes of similar mass. So we've replaced a carbon with an oxygen compared with the alkanes, but again, the oxygen doesn't have the other hydrogens on it, so the mass is pretty similar. So a dimethyl ether might act a lot like propane in terms of its boiling point, for instance. All right, I mentioned it in passing before, but here's a slide where we address it directly. Solubility of alcohols and ethers in water. Alcohols and ethers are more soluble in water than alkanes because the oxygen atom can help to participate in hydrogen bonding with the water. So for the alcohols, if we have a small alcohol, 1 to 3 carbons, they're typically completely soluble in water. So things like methanol, ethanol, propanol, or isopropanol, you tend to get what's called miscibility. They're soluble with water in any amount. Once we hit 4 carbons, then the solubility goes down. 5 or more carbons, they're typically insoluble for the alcohols because they have a significant alkyl group now, and those alkyl groups like to interact, and it lessens the ability of the OH group to participate in hydrogen bonding with the water. For ethers containing up to 4 carbon atoms are slightly soluble in water, and that's because if they have small alkyl groups, they do have those 2 lone pairs, as I mentioned in the previous slide, and they can be hydrogen bond acceptors from the water, although they can't be hydrogen bond donors because they don't have a hydrogen bonded directly to their oxygen. They can be hydrogen bond acceptors, so it works a little bit for small ethers to be slightly soluble in water. And here we see an example of that with methyl alcohol and water. As I said, miscibility is the term that we use for an alcohol like this that can dissolve in any amount with any ratio of methyl alcohol to water. And the reason it does such a nice job is it can really participate well in hydrogen bondings. It can be a hydrogen bond donor, as we see the methanol OH group donating a hydrogen to the far right bottom oxygen lone pair, and then it can be a hydrogen bond acceptor as well, as we see the lone pairs on the oxygen of the methyl alcohol accepting hydrogens from the 2 top water molecules. In the case of dimethyl ether, it doesn't work quite nearly as well because we don't have any ability to hydrogen bond donate, but we do have those 2 lone pairs on the oxygen. They aren't shown, but they are there if you draw the Lewis structures, and as a result of those 2 lone pairs, we can accept hydrogen bonds from neighboring water molecules. So that does allow something like dimethyl ether to have limited solubility in water, whereas methanol or methyl alcohol, as it says on the slide, has miscibility, is soluble completely in water. Now, I certainly don't expect you to memorize boiling points, but looking at these trends, I wanted to give you some actual numbers. So if we look at methanol, it's the simplest alcohol, the smallest, and it has a pretty high boiling point for something so small compared with methane, as we remember that had a boiling point in the negative 100 degrees Celsius range. Here we have something that's positive 65 degrees Celsius and perfectly soluble in any amount with water. As we move up to ethanol, now we've gotten a little bigger. We're 2 carbon atoms now, and the hydrogens that go along with that, and our boiling points increased a little bit up to 78. As we continue to increase for the straight chain terminal alkanes, we have a continued increase in boiling point as we increase the number of carbon atoms, but certainly a rapid decrease in solubility in water to become essentially insoluble once we have 5 or more carbons. If we look down below in the table, we have now the ethers to consider, and as you see, those boiling points are quite a bit lower. So the 2 carbon ether, dimethyl ether, has a negative 23 degrees Celsius compared with the 2 carbon alcohol being a positive 78 degrees Celsius boiling point. As we increase in size, because of those London or dispersion forces, we do get higher boiling points just because of those nonpolar interactions, but again, still significantly lower than the alcohols. We also see only slight solubility for our simplest ethers, and then they become rapidly insoluble, just like we saw with the alcohols as they get 5 carbons or more total in the ether. So now that you have some actual numbers to deal with, hopefully you can recognize just how important that OH group of the alcohol is in allowing a much higher boiling point and much greater water solubility than even the ethers, which are also oxygen containing, although not hydroxyl group containing compounds. Okay, finally now let's talk about phenol. We talked about the regular old alcohols, but we didn't mention this one. Phenol is actually soluble in water. That's unusual for something with an aromatic ring portion to it, especially something that's just the OH on an aromatic ring. But that hydroxyl group is available enough that it can undergo hydrogen bonding with water. Also, it ionizes slightly, so it's actually a weak acid. That's not why it's a disinfectant, but it is a noticeable feature of it. It does dissociate, and so it can be corrosive and irritating to the skin as a result. And we see here that weak acid plus water in equilibrium with the weak acid anion, in this case the phenolate ion, and the proton, which is now sat on a lone pair of that water to become the hydronium ion. So there we have it, our weak acid plus water in equilibrium with weak base, the acid anion, plus the hydronium ion. This should look very familiar from General Organic Biochemistry 1, where you saw this sort of thing probably, if you were with me, definitely, but most courses would show it at the end of the General Organic Biochemistry 1 semester. All right, before we leave our physical property subtopic, let's end with a few learning checks. So in this first learning check, which compound would have the higher boiling point, ethyl methyl ether or 1-propanol? And please explain your answer. So stop the video here while you think that through and start us back up when you're ready to check your answer. So if you recall from a few slides back, 1-propanol would have 3 carbon atoms, right, from propane, prop being the prefix for 3 carbon atoms, and can form hydrogen bonds with water. It was in that 1 to 3 range, and it gives, therefore, a higher boiling point because it can form the hydrogen bonds with itself, and greater water solubility because it can form the hydrogen bonds with water. For the ethyl methyl ether, it's roughly the same molecular weight. It has the 3 carbons also plus the oxygen, but it forms fewer hydrogen bonds with water due to its structure. It also can't hydrogen bond with itself, so therefore we would expect a much lower boiling point for ethyl methyl ether. So if we're strictly following what the question wants, the higher boiling point goes with 1-propanol because 1-propanol can hydrogen bond with other 1-propanol molecules in a sample, whereas ethyl methyl ether, although roughly the same mass, cannot hydrogen bond. It only can undergo the nonpolar London or dispersion forces. Okay, and our final learning check, which compound would be more soluble in water, ethanol or 2-pentanol? And then please explain your reasoning. So pause the video here while you reason that out and start back up when you're ready to check your work. Good luck. Okay, and there we have it. Ethanol has 2 carbon atoms in its chain. It is more soluble than pentanol with 5 carbons. The longer the alkyl chain, the less soluble the alcohol is in water. And if you remember, once we hit 5 carbons in the alkyl chain, we essentially said those alcohols are insoluble in water. So it pays to be an alcohol so that you have any chance of hydrogen bonding with water, but it pays in particular to be a small alkyl chain alcohol because then you're much more likely to be able to hydrogen bond well with water. And in the case of ethanol, you can be soluble with any amount of water. 1 to 3 carbons, we said those alcohols are miscible. 4 carbons, we said they're slightly soluble, and then 5 or more, we said they're essentially insoluble. So it makes sense that ethanol would be more soluble in water than 2-pentanol. If you had any trouble with either of those learning checks or just any of the material from the chapter, please do reach out for some help. But otherwise, if things are going well, I'll see you in the next and last topic for Chapter 13.